After Einstein proposed his theory to explain the photoelectric effect, it was over 10 years before the predictions from his equations and theory are actually measured and confirmed in more detail. And the person who actually carried out the measurement was the same person who did the oil drop experiments. Taking a while to clear this up. Okay, and that was in the year 1914. Robert Millikan, as in Millikan's oil drop experiments. So he carried out the photoelectric measurement in more detail to measure how current and voltage, how these change with things like light intensity, frequency, and how the stopping potential change with all these. So let's look at one of his graphs. Let's look at one of his graphs. I'll draw it here. So the vertical axis is, say, the current, and the horizontal axis is the voltage. And suppose that we use blue light for this particular measurement. So using the blue light, lots of little blue photons, let's see what he did. Right, okay. He connected this to voltage. That's negative pole. Connected to here. Okay, so in this case we have minus here and plus here. And he varies this voltage, which I'll call V, varies this voltage, and measured the currents. And the graph that he plotted looked like this. When there's no voltage, when there's zero voltage, there would be a small current. There's a small current at zero voltage, because even when there's no voltage between the two plates, the blue photons are able to have enough energy both to eject the electrons to overcome the work function, and still have some left for the kinetic energy. So it is this remaining kinetic energy that supplies the current. Right, so it means it's like a kind of a battery with the light providing the energy that is turned into an electrical energy. Okay, so in a way, this is like a device that converts light energy into electricity. And as voltage is increased, suppose that we use battery with a bigger voltage, or a battery that we can adjust the voltage, the graph looks like this. As voltage is increased, current would increase, but at some point it stops increasing. Why does it stop increasing? it might be easier to understand why it's a bit lower in the beginning. In the beginning, not all of the current ejected when the voltage between these two metals are zero, not all of the current ejected, the electrons emitted, would reach the positive pole. Some may just go sideways and hit the wall. But as we increase the voltage, this becomes more positive, and eventually it will attract all electrons. So those electrons that actually go sideways would be attracted back towards the forward direction. So eventually, when all the electrons are attracted to the positive pole, the current doesn't change anymore, because even if we increase the voltage further, we still have the same number of electrons every second coming out from the plane. So that explains why it flattens off after a while. So this part must be because some of the electrons are hitting the walls, going sideways. Now if we reverse the battery and make this negative, then the negative plate will slow down the electron. Okay, we repel the electrons, and those will slow down, so fewer electrons will reach here. So as the reverse voltage is increased, the current would decrease until eventually there must be a value where the electrons will stop when it just reach this plate, and that would be the stopping potential, which we call Vs. Put a minus sign here to represent the reverse voltage. So this is the kind of graph that Millikan actually obtained. So the graph looks like this. And this was for a particular brightness of the blue light. Now what he found was that when he changed the brightness, let's say when he lowered the brightness, he finds that the current becomes smaller. So this is lower intensity of the light. Maybe I'll just use a simpler word: when the light is dimmer. So when the light is dimmer, the current is lower. Why would the current be lower? Because when the light is dimmer, it means that there must be fewer photons coming in every second. So therefore there will be fewer electrons emitted every second, and therefore the current is smaller. Okay, so for lower voltage, the current will come down, and when the voltage is reversed, the current will continue to fall, and eventually the current falls to zero at the same stopping potential. And that's as we would expect from Einstein's theory and earlier work on photoelectric measurement, that the stopping potential, or the maximum or the kinetic energy, does not depend on the brightness of the light. Okay, and we now understand from Einstein's theory that it is because even if the light is less bright, each photon still have the same energy, as long as it's the same color or frequency of the light. So therefore it must come down to the same point. And if we use a brighter light, if we make the blue light brighter, we would expect that the current should increase, and that was indeed what's observed. Current should increase because with a brighter light we get more photons. It means we get more photons every second coming in, and therefore more electrons are emitted every second, and therefore the current is higher. And as the voltage is decreased, current starts to drop, and when the voltage is reversed, current continues to drop, and at a certain voltage the current drops to zero, and that voltage happens to be exactly the same as before. Stopping potential, again for the same reason. Even if you have for brighter light, You have more photons, but each photon still has the same energy. So therefore, the electron emitted will have the same maximum kinetic energy. Therefore, you need the same voltage to stop it. So that's one observation of Millikan. Now the next observation, let's look at the next one. Again, current voltage observation. And let's start with that a similar curve. This time I'm going to use blue to represent the blue light. So let's say this curve is just the same as this curve. I'll call this curve maybe B for blue. I'm just copying out the same curve here. And but in this other graph, what was done was that after doing it once, doing measurement once for using blue light, a different color light was used. Let's say a green light was used. So but it was green light of a similar brightness, so that's green light of similar brightness, so that the final current is similar, right? It's not so different. But as the voltage is reduced and then reversed, it was found that the current comes to zero at a different voltage, at a lower voltage. And we actually understand why. Now, from Einstein's theory, is because if we use green light has a lower frequency, therefore the photon has a smaller, each photon has a smaller energy. So after overcoming the work function, there will be less energy left for the kinetic energy. So that's why we need a smaller potential to stop it. And in a similar way, when violet light was used, it was found that again, if we use a violet light of a similar brightness, the final current is similar. But as we lower and reduce the voltage, it was found that you need a bigger potential to stop the electron. And we understand that that's because violet light has a higher frequency than blue or green light. So each photon has higher energy than the blue or green photon. Therefore, after ejecting the electron, there would be more kinetic energy. So that's why you need a higher voltage to stop this current. So let me just write down what this means. So mainly the green light is lower frequency, and the purple light has a higher frequency. So that's why you have the changing stopping potential. So there are these two results. Now, but there's one more result that I need to talk about. Maybe I'll talk about it in the next video.